Okay, good. In the old days, used to be where we'd be having tea and biscuits and chatting over them.
So are there now people on YouTube who are watching us?
Let's see. Not now, but usually we have like around 10 people on YouTube.
Okay. Do we know who they are?
Well, we know their handle. But maybe this time they choose to join the Zoom meeting, because I think we have more people in the Zoom meeting this time.
We hope.
Yes, we're getting numbers in. We've still got 2 minutes to go, according to my my clock.
Yep.
I should perhaps say that my computer has crashed twice in the last 2 days, and I've had to restart it to get back to the internet. So if I suddenly vanish, that will be the cause. But it has always come back. It's quite peculiar. It hasn't done this before.
I won't notice a thing, probably.
No, you'll just carry on obliviously to it.
In fact, I would carry on obliviously even if the entire Zoom call stopped, probably, or if everyone left, because all I can see on my screen is my own PowerPoint slides when I'm sharing the screen.
Yeah.
So forgive me if I look slightly dazed or disengaged as I'm I'm going through the slides.
So when you say you studied at the University of Canterbury, I presume that's University of Canterbury, New Zealand.
Absolutely, not to be confused with other Canterburys.
Well, that's what I was thinking. Yeah. Okay. Right.
Karl Popper's University.
Oh, of course. Yeah. Yeah.
There's still a building called the Popper Building, which is the one I was trained in while I was there.
Mm-hmm. That was a long time ago he was there.
Yeah, long time ago, but he still left his mark. When I did my historiography module there, it was very Popperian. The idea was you do history by coming up with a bold conjecture, and then you draw lots of inferences from it, or sub-hypotheses, and then you test them out. That's how you did history.
Right. Popper's historical method. Yes, right, okay.
Yeah.
Right, it's now 5 o'clock London time, so I think we'll begin. So if everybody apart from me and the speaker go to mute, that would be very helpful as we start the first SHAC seminar of 2026 in our continuing series, which we began during the pandemic and thought it was a good idea to continue once the pandemic had passed. So there's the Zoom link, which many of you are on, and if you want to participate in discussion after the meeting, after Michael's spoken, please put a note in the chat box and I'll invite you to participate. If you're on YouTube, we can't do that for various technical reasons, so put your question into the YouTube chat box and it will be sent to me. So the talk will be sort of 20 to 30 minutes and then 30 minutes of discussion. So this month's presenter is Dr. Michael Bycroft, who is a historian of early modern Europe with a particular interest in France and the physical sciences. And his book, Gems and a New Science, Matter and Value in the Scientific Revolution, will be published next week by University of Chicago Press. Is that your first book?
It's my first monograph. Yes, it's been a long time in the making.
Excellent. Michael studied at the University of Canterbury, then the University of Cambridge, and then the Max Planck Institute for History of Science in Berlin. And he's now Associate Professor of the History of Science and Technology in the History Department at the University of Warwick. And he's going to talk to us on the topic of his book, I think, Gems and the Crafts in the Chemical Revolution. Michael, the floor is yours.
Excellent. Thanks very much, Frank. Thanks very much for the invitation and the introduction. I am now trying to find my PowerPoints so that I can share it with everyone. It seems to have disappeared from my options. Just a moment. Share screen. Window. No, it's not showing up. It was doing that 5 minutes ago, but now it seems to be failing. I'm going to open it again. See if that works. Share screen. Yes. Frank, is that working? Frank, can you?
Yes, it's working.
It is working. Brilliant. Okay. Excellent. Yes, thanks very much, Frank, for the invitation and the introduction. I really couldn't imagine a better audience for this particular presentation, or a better format, actually, a short talk followed by an interesting discussion. As Frank said, this presentation is part of a book project. Unfortunately, the book is already out, so all of my mistakes that I'm sure you'll pick up on can't be corrected, at least not for this edition of the book. But I hope to draw out some broader lessons that might be useful for people working on chemistry in other times and places and on other materials. So I've been told by my publisher to relentlessly publish this monograph, relentlessly plug, I should say, this monograph. So I hereby plug it. It's due out in February 2026, which is quite soon. So there you go. I won't give the whole thing away because I do want you to actually go and read it, go away and read it. Suffice to say that the basic idea, the headline idea, is that gems are scientific objects. They're part of scientific history. They're not just part of economic history and jewelry history, although they definitely are. And although there are interesting crossovers between these different dimensions of gem history, the basic claim here is that gems are a class of materials that historians of science should take seriously, and not just historians of chemistry. So what I'm going to present today is one chapter from the book, the one on the chemical revolution, but there are other chapters on crystallography, on experimental philosophy, on natural history, on mineralogy, and so on. Chapters that span the early modern period, span roughly the period that's sometimes called the scientific revolution, from around 1500 to 1800. So that's the basic idea. Gems are scientific objects. But I also want to make a couple of bigger arguments about the history of science and about how science changes. And those bigger points are indicated by the word matter and the word value in the subtitle. Today, I'm going to talk about matter. Try to explain to you what I'm on about when I include matter in the title of this book. By way of beginning, consider this quote from Axel Fredrik Cronstedt, so the leading mineral chemist in Europe, arguably, in the 1750s, when he wrote these words. This is from Essai de Nouvelle Minéralogie. So this is a translation from the original Swedish. So the way I arrived at this topic was by researching the history of French science and finding that I couldn't really understand what was going in France without understanding what was going on in Germany and Sweden. So I began reading translations of German and Swedish works into French. And that's the basis for a lot, although not all, of what I'm going to say today. So the species in this division, so he's talking about the category of siliceous earths, which includes lots of what we would call gemstones. These species do differ amongst themselves, but regarding their behavior in fire and other chemical tests, we cannot easily determine the difference. And rather than describing these tests, because I haven't done any, I can do no more than treat them as simple bodies, no matter how composed they might be. Sorry for the typo at the end there. So the leading mineral chemist in Europe in the 1750s was just stumped by gemstones. Although he was capable of decomposing lots of other minerals, that is, dividing them into their components, physically combining them into their components in a laboratory, he had cracked lots of other nuts. He had become an expert on the use of the blowpipe. He had discovered new elements like nickel, but gems defeated him. A few decades later, that had changed pretty much beyond recognition. If we look at René Just-Houi's textbook on mineralogy, the treatise on mineralogy, published in Paris in 1801, we find that he is very confident about the components of gemstones. So when writing about the chemical characteristics of emerald, for instance, he tells us that there's such and such a quantity of silice, what I guess we would now call quartz, such and such a quantity of alumine or aluminium oxide, glucine, or what then became known as beryllia, what we might call beryllium oxide, and so on and so forth. So he knows what's in emerald, he knows how much of each of the components is in emerald, and he's also able to compare those numbers with the similar numbers for other stones, such as aquamarine, and on the basis of that comparison, he can say that these two stones are really the same species. That the emerald from Peru and the aquamarine from Siberia are really basically the same thing, in part because of their chemical composition. So in the last few decades of the 18th century, European naturalists discovered gem decomposition, discovered how to break gems into their components. A fairly dramatic change in a fairly short period of time. The analysis of gemstones is one of the untold stories of the chemical revolution. A couple of caveats to that statement. Different parts of the story have been told by different historians. Christine Lehmann and her work on diamonds is very significant. Stephen Irish and his work on corundum. Jonathan Simon and his work on mineral collections also touches on gemstones. But what we're lacking is a synthesis of this broad trend towards decomposing gemstones. My other caveat is that I'm using the phrase chemical revolution in a slightly unorthodox way, which will be familiar to some of you, but maybe less familiar to others of you. So I'm not going to be talking about the great battle between the phlogistionists and the anti-phlogistionists, or the followers of Lavoisier and his enemies, but I will be talking about compositionism, the idea that the way to understand chemical substances is in terms of their components, where the components are the parts of them that can be isolated in the laboratory. It's been argued, I think convincingly, that this was a relatively new way of thinking about chemical substances that became much more pronounced in the latter part of the 18th century than it had been previously. So with those caveats in place, the question is how to explain the shift from Cronstedt to Houy, how to tell the story of gem analysis. Clearly, part of the story must be the crafts of gemstones. The role of crafts in chemical theory is one of the really big themes of the historiography of 18th century chemistry over the last few decades. Whether it's presented in terms of the relationship between scholars and artisans, between the mind and the hand, in terms of technoscience or scientific expertise, we have lots of studies of the relationship between chemistry and gold making, between chemistry and mining, chemistry and porcelain making, etc. So why not a study of chemistry and the arts of gems, chemistry and gem trading, gem cutting, gem polishing? And these crafts are definitely part of the story. They definitely played a role in gem analysis. And the text on the slide is a small example of that, small but famous example. So Lavoisier, of course, a well-known chemist, also well-known for destroying diamonds, for helping to demonstrate that diamonds are combustible. He did this in a furnace and then with a burning mirror. Also, characteristically made precise measurements of the diamonds before and after they were heated. So you can see some of that kind of argumentation in the upper text here. So there Lavoisier is saying that he started with 19 5/8 grains of diamond and ended up with 16.5 grains of diamond plus some residue, which he goes on to describe. So the kind of thing for which Lavoisier is famous, precise measurements of the inputs and outputs of experiment. The interesting thing is that you find exactly the same level of precision in account books of jewelers from the same period in France. So the bottom image shows one such account book showing a jewel weighed down to 1/32 of a carat, which is the same as 1/8 of a grain. And we know, because Lavoisier tells us, that he did this experiment in the presence of jewelers or gem cutters. It's not quite clear from his terms which category they fit into, but they're definitely gem experts. And we know that the experiment that he was doing was one that had already been done by gem cutters, as I'll explain in a moment. So this is the kind of thing that is fairly typical of lots of research on 18th century chemistry. Find an interesting theoretical development like the combustion of diamonds and try to link it up to craftspeople. So I could go on and give more examples of that and show how the chemistry of gems depended on the crafts of gems. But the more I went into that topic, the more I found that my approach was incomplete. It wasn't wrong, but it was incomplete. The basic point being that the interaction between different crafts was just as important as the interaction between the crafts on the one hand and chemical theory on the other hand. So hand-hand coordination, the interaction between hand and hand, was just as important as the interaction between hand and mind. That means several things. It means that at each step in the innovation in gem analysis, multiple crafts were involved. Jewelry and porcelain in one case, glass and porcelain in another case. They weren't all involved in every stage, but there were multiple ones involved in each stage. Also, different crafts lent themselves to different kinds of chemical analysis. So one kind of chemical analysis is just to literally take a substance apart. Other kinds of analysis could be used to determine the components of gems. So I find these useful historians categories for understanding what was going on in 18th century chemistry. The words analysis and decomposition were not used consistently in this way at the time, but I find it useful to think of analysis as the umbrella category for the effort to identify the components of gems, and decomposition a term for the specific practice of taking gems apart in order to identify their components. There are other ways of doing the same thing. Different crafts lent themselves to different techniques. As a result, when different crafts came together, different kinds of analysis came together, often resulting in somewhat new sorts of analysis. Also, this was embedded in wider changes in European chemistry. So these interactions between crafts had a geographical dimension, since different regions of Europe specialized in different crafts. So a merging of craft was often a merging of traditions from different parts of Europe. These interactions also had a disciplinary dimension. Often what looks on the surface like a merging of two different disciplines, like mineralogy and the natural history of minerals, often that is bound up with a merging of two or more different crafts. And all of that, I think, is reasonably summed up with the notion that chemistry was greater than the sum of its parts. That is the slogan for this talk. So those are my theses. I could go through a large number of examples to support them, but I'm only going to give 3 and then end with some conclusions. And I'll whip through the examples fairly quickly because I think I only have 10 minutes or so left. First example is German mining chemistry in the first half of the 18th century. It's well established. It's been known since at least 1981, thanks to Theodore Porter's article. It's been known for a long time that mining helped to drive chemical theory in the 18th century, and in particular that it helped to drive analysis by decomposition. After all, mining chemistry involved assaying mineral ores, metallic ores, and assayers spent much of their time trying to separate those ores into their components and then weighing those components to find out precisely how profitable a given ore would be. So assayers were natural chemical decomposers. So it makes sense that mining chemistry played a big role in changing ideas and changing techniques to do with chemical composition. However, what worked for metals didn't necessarily work for gems. And so to analyze gems, as they sometimes did, German mining chemists sometimes drew on other crafts and other techniques, which they used in tandem with techniques drawn from mining. Henkel's work is a good example. So his introduction to mineralogy is often treated by Porter and others as a characteristic example of German mining chemistry. Henkel's teaching in Freiburg is also seen as a seed for the Freiburg Mining Academy, established in 1765. And Henkel definitely insisted on the importance of decomposition in studying minerals and literally taking them apart. He talked about chemical anatomy, for instance. And he was often fairly scornful of external or superficial qualities of minerals like their color or their hardness. But that's not the approach that he used when he came to gems. When he talked about gems, he used what he called analogy, analysis by analogy. So he would classify mineral gems and related minerals not by taking them apart, but by subjecting them to various chemical tests, especially acid and fire, and checking whether they behave like other minerals. So he argues that rock crystal, for example, must be made of flint because pieces of rock crystal responds in the same way as flint to acid and fire. So he hasn't taken rock crystal apart literally, but he has compared its chemical behavior to other minerals. So that's a method of analysis, a way of finding out about the components of quartz, which doesn't involve decomposition. And when he came to deal with gems, he would argue by analogy using techniques which are a mixture of mining techniques and gem cutting techniques. So in 1737, he identifies what he called true Saxon topaz, which he argues was previously confused with yellow varieties of quartz or fluorspar. There you can see a piece of true Saxon topaz, which I have, well, the image of which I have acquired thanks to the Freiburg Mining Academy, its present-day manifestation. And in order to make this identification, Henkel does talk about the chemical properties of the stone. He talks about its fusibility or the difficulty of fusing it compared to quartz, but he also talks about its hardness. So one of these properties that he scorns in other texts as being superficial or external, he is very happy to use it in this case, and he's relying on the judgments of cutters for his data on hardness. So there were Saxon gem cutters who were cutting Saxon topaz in the form of diamonds, possibly or almost certainly to pass them off as real diamonds. but also simply to valorize these local stones. So cutters were the ultimate judges of the hardness of stones in this period, not just in Germany, but elsewhere. There's loads of evidence for that. They were grinding these stones on their grindstones. And if you do that on a daily basis, you become extremely sensitive to their hardness. So in order to determine the identity and the composition of Saxon topaz, Henkel was combining different crafts. Example number 2 is the discovery of the combustion of diamonds, which I mentioned briefly at the start. And here I want to focus on the instruments used in the experiments, instruments which came partly from diamond cutters and partly from porcelain makers. And here you can probably tell that I have small children who use felt pens, and I've come to the conclusion that there's no pedagogical problem that is too difficult for a set of felt pen style diagrams. So the first of these shows the first real French effort to destroy diamonds, the first successful French effort to destroy diamonds, and it was done by Jean d'Arcy. He reported this to the Académie Royale des Sciences in 1768, and what he had done was heat the diamonds in his porcelain furnace, and within that furnace, the diamonds were surrounded by a sphere of unfired porcelain. All this was part of Darcy's broader effort to discover the secret of hard paste porcelain, which meant heating a huge number and variety of different minerals. So it wasn't long before he got around to trying diamonds, and the diamonds were destroyed in this process. The next question was, why are they destroyed? Did they evaporate like water? Did they shatter like tiny particles due to some kind of thermal shock? Or did they combust? Did they burn in air like wood or like charcoal? And the way to test, or to answer that question, sorry, was to find a way of excluding the air from the vessel. So the reasoning being that if air was necessary to the destruction of diamonds, then it must be a case of a combustion rather than evaporation or shattering. So the key experiment here, the key effort to shield the diamonds from air was done in the laboratory of Hilaire-Marin Roel. This was reported by Lavoisier in his first memoir on the destruction of diamonds. It was done with the help of Maillard. We don't know much about this man except that he was a skilled jeweler. That's Lavoisier's phrase. And Maillard supplied the apparatus for shielding the diamonds. He also supplied the diamonds. This was a kind of bet. He was supplying the diamonds, and he was convinced that the diamonds would survive the experiment. So his money, his objects were on the line. And what he did was to take those 3 diamonds, they're in green at the center of that image. He placed them in a pipe. He stuffed that pipe with charcoal. He sealed it with a mixture of sand and salty water. He placed that in a bath of chalk, which was in turn in a crucible. And then he surrounded that apparatus with a sphere or semi-sphere made up of 2 other crucibles, which were also sealed with sand and salty water. So you got this multi-layered defense mechanism to protect the diamonds from the intruding air. So this was placed in a furnace in Roel's laboratory. The furnace was fired for hours on end. It was hot enough to actually start melting the furnace. At the end of a number of hours, this whole apparatus was taken apart, and lo and behold, the diamonds had survived. So this was at least for Macaire and Lavoisier and others, this was a strong indication that it was the air which was responsible for the destruction of the diamond as well as the heat, and therefore that this was a case of combustion. But that wasn't the end of the matter, because now the question was how to reconcile the jeweler's experiment, which I've just described, with the porcelain maker's experiment, the one I showed on the previous slide. Why had the diamond been shielded by the pipe arrangement, but not by that porcelain sphere you saw on the previous slide? And to answer that question, the two types of experiment and two types of craft had to be combined. The first thing that was done by Macaire was to repeat the jeweler's experiment, but in a much more powerful furnace. This was the Sèvres porcelain furnace, and Macaire found that the diamond survived in this case as well. So it's not just that Darcy had an unusually strong furnace. That doesn't explain why his diamonds were destroyed. Various further experiments were done. All of this is reported by Lavoisier in his first memoir there. But the ultimate solution that was found was to fire the porcelain sphere before heating the diamonds. So in Darcy's first experiment, he had used a porcelain paste, an unfired piece of porcelain paste in which he placed the diamonds and which he then heated. I guess as you would do if you were a porcelain maker. For a porcelain maker, the whole point of firing porcelain, or heating porcelain, sorry, is to fire it, to turn a paste into a hard piece of porcelain, a finished piece of porcelain. So once the pre-fired porcelain was used, the diamonds were protected. Also, it was found that charcoal helped with this. So with the porcelain sphere and this charcoal inside the porcelain sphere, the diamonds survive the experiment. So is this an example of scholars interacting with artisans or with the crafts? Yes, it certainly is, but it's also an example of different crafts interacting with each other. Diamond cutters and porcelain makers contributed to something that went beyond both groups. Example number 3. I'm not going to ask you to read this out. I'm not going to read it out. I'm not going to ask you to read it. Louis-Nicolas Vauquelin was a French chemist who worked at the Maison des Mines, the House of Mines, in the 1790s. This is a footnote from my book, which seemed to me the easiest way of impressing you with the large number of papers Vauquelin wrote about gemstones. And in each of these cases, he tried to analyze the gemstone, work out what its chemical components were, and he did this by decomposing the stones. He did topaz, peridot, garnets, chrysolite, ruby, emerald, etc., etc. He saw this as a coherent project, so he even had a name for it, lithogeognosy. He had a general procedure which he described in 1799, reflections on the analysis of stones and the results of several analyses of stones. He saw himself as part of a longer tradition. He was drawing on work by Torben Bergman in Sweden and also by Klaproth in Germany, and he definitely acknowledged his debt to them. So this is a large-scale project of the chemical decomposition of gemstones. How did he manage this? Well, partly it was just a matter of importing into France techniques that had been developed in Germany and Sweden, but it was also a matter of combining those techniques with French crystallography. So on the left here, you see some items from the collection of René Just Houy. So while Vauquelin was doing his chemical analyses, Houy was developing the science of crystallography, or helping to develop it. And the two worked very closely together. They were both employed at the House of Mines for a time. Houy then moved to the Museum of Natural History in 1802, if I remember correctly. Vauquelin then moved to the same place a couple of years later. So this was a sustained collaboration. And the analysis of beryl is a good example of how they worked together. So up until this point, as I said at the start, Siberian aquamarine and Colombian emerald were seen as distinct species. We noticed a geometrical resemblance between the two species, He then asked his colleague Vauquelin to check this hypothesis by chemically analyzing aquamarine. Vauquelin does the analysis. He not only finds that his analysis of aquamarine matches up with an earlier analysis of emerald done by Klaproth, but he also finds a new earth. He didn't give a name to it. We would now call it beryllia or beryllium oxide. His next step, or the next obvious thing to do, was to look for this new earth in emerald as well. So he repeats Klaproth's analysis, but does it slightly differently and more rigorously, and finds beryllia and emerald also. So a good example of Vauquelin and Hauy working together to sort out the chemical identity as well as the crystallographic identity of emerald and aquamarine. I quote Vauquelin: "This satisfying agreement between the two apparently distinct sciences shows that at the same time they are founded on sound principles." Vauquelin was using crystallography as part of his analytical technique, I would argue. Of course, in the following decades, it turned out that things were a bit more complicated than that. So chemistry and crystallography turned out to be a bit harder to reconcile than Vauquelin thought at the time. And there's lots of discussion by historians of chemistry and physics and crystallography in the early 19th century about how that was worked out. But I think that has distracted a little bit from the question of how this reconciliation seemed plausible in the first place. It turned out to be very difficult to bring chemistry and crystallography to the same table, bring them into contact in the first place. In the French case, it meant joining up two quite different traditions, two quite different 18th century scientific traditions. One which was called mineralogie, and the other one called the Histoire naturelle des minéraux. You find this distinction drawn very sharply in the articles in the Great Encyclopedia of Diderot and d'Alembert. On the one hand, the natural historian of minerals, Louis-Jean-Marie d'Aubenton. On the one hand, a mineralogist, the Baron d'Holbach. The two traditions are practiced at different institutions, at the Jardin du Roi and the Muséum National d'Histoire Naturelle for the natural history of minerals, the École des Mines, the Maison des Mines for mineralogy. Mineralogy tends to classify minerals by chemistry. Natural history of minerals classifies them by color, hardness, and crystal form. So there are all these differences between the two traditions. But as part of that mixture, perhaps not foundational, but certainly part of that mixture, there is a distinction between two different craft traditions. So mineralogy draws primarily on mining chemistry, whereas the natural history of minerals draws primarily on the crafts of gems, trading and cutting and collecting. So what Vauquelin and Hauy are doing in their collaboration is joining up those two craft traditions. So those are three examples. If I gave a couple more examples and then strung them all together, you would end up with something like this. So this is my potted history of gem analysis in the course of the 18th century. So first of all, you find mining chemists like Henkel transferring mining techniques to the case of gems and coming up with forms of analysis such as analogy. The next generation, you find porcelain making becoming part of the same tradition. So Johann Heinrich Pott, a follower of Henkel, analyzes gems with this techniques which he calls resolution, which is a bit like Henkel's, but is slightly different because Pott is classifying gemstones not according to what they're made of, but according to what they make. So what kind of porcelain does this mineral make? That's his key question. And he uses that as a basis for grouping gems into categories. Next, we find Lavoisier and his colleagues in France who are adopting this German tradition of mining and porcelain making and mining chemistry and porcelain chemistry and turning that to their own purposes. Another step which I have missed out is Torben Bergman, a Swedish chemist who gives really the first serious European effort to decompose gemstones And there he's partly drawing on Swedish metal mining, which I guess is the craft that people think of when they think about 18th century Swedish chemistry, but he's also drawing on pharmacy, he's also drawing on glass making, and without those, he actually couldn't have achieved the analytical procedure that he described in 1777. And finally, crystallographic chemistry is an effort to supplement those decompositions of gemstones with crystallography, and just to corroborate the chemical decompositions, but also to point the way towards the discovery of new components. So the analysis of gems was done by synthesizing the crafts. That is the take-home lesson. Chemists took gems apart by bringing the crafts together. I said I would try and draw some broader conclusions at the end. So I have some queries. So like an 18th or 17th century natural philosopher, I have some questions where I have hunches about the answers, but I can't prove my answers. So let me call them queries. How much of 18th century chemistry was driven by the influx of trained pharmacists into the mining industry? So this was true of Vauquelin. He was trained as a pharmacist, but then ends up working with the newly founded School of Mines. And that's the institutional, the social mechanism, which is bringing together pharmacy and mining in the case of Vauquelin. And it strikes me that there are a number of other key 18th century chemists who are part of that same trend, who have similar career paths. Klaproth in Germany, Margraf, Georges Balthazar Sage, who is another key figure in the French case just before Hauy and Vauquelin. The point here being that the 18th century mining industry wasn't just about bringing together mining theorists with mining practitioners. It was also about bringing together different sorts of practitioner, pharmacists with miners. Did the shift to a compositionist view of substances work out differently for different materials? By the compositionist view of substances, I mean this view which says that each substance is just a congeries of different components, each of which can be isolated in the laboratory and which can be measured and perhaps recombined. Did the shift to this view work out differently for different materials? That's a natural question to ask, since we've seen that different crafts worked out differently for chemistry and different crafts were anchored in different materials. So is there a slightly different story to tell for plants, for earth, for salts, etc., in terms of the shift towards compositionism? Would this help to reconcile historians who see compositionism as emerging in the late 18th century on the one hand, with historians who find compositionism as early as the 13th century? So some historians of alchemy, like William Newman, have argued that already in the 13th century, alchemists were making an effort to define metals in terms of their components and were, as they saw it, isolating those components in the laboratory. One way to reconcile these different historians is to say that something was happening for metals in the 13th century, which would happen much later for other materials, like earths and salts. Second to last question, can we think of the chemical revolution as the result of the effort to extend to gases methods already applied to liquids and solids? So in a separate paper, I've argued for a similar pattern in other sciences. So around 1800 in astronomy, we find that astronomical methods, for example, telescopes, which had been applied to the solar system in the 17th century, are being adapted to the world beyond the solar system, to galaxies and nebulae and so on. And those techniques are genuinely being adapted, are changing in the process. Can we tell a similar story about late 18th century chemistry? Is it not so much an invention of lots of new methods, but an adaptation of older methods to new materials, in particular to gases? And finally, underlying all of this, the question is, what does it mean to be a transmaterialist, not just a materialist, about the history of science? So just to unpack that a little bit, so a great deal of research in the history of science, not just chemistry, not just early modern, over the last, I don't know, 30 years or so, could be labeled materialist. The idea has been to link up the material world with the mental world, sometimes by looking at the crafts, sometimes by focusing on material substances, sometimes focusing on material hardware, like instruments or natural history collections, sometimes focusing on the natural world itself. Yet perhaps this has always been done in a somewhat piecemeal way, in the way that we've got lots of studies of the relationship between chemical theory and this craft, or of that craft, or the other craft, but few studies of the relationship between the crafts themselves. Perhaps that same basic pattern can be found elsewhere among historians of science. Perhaps we need more work on the relationship between instruments on the one hand and natural history collections on the other hand, for example. So those are my queries. I'm really looking forward to your questions.
Thank you, Michael. That was really, really interesting indeed. And people are already putting up the sort of funny symbols that one gets on Zoom. Okay, so as I said at the beginning, those of you who are on Zoom, indicate in the chat box that you want to ask a question. Those of you who are in YouTube, put the question in the text in the chat box there, and it'll be passed to me. While you're thinking of your own question, I'm going to exercise my chair's normal prerogative and ask the first question. As it happens, in the past couple of weeks or so, I've been looking at Humphrey Davy's experiments in Florence using the enormous lens of the 1690s lens of the Grand Duke of Tuscany, and Davy used that in the spring of 1814 to decompose or destroy diamonds. And bearing in mind the work of Lavoisier and the other people you've talked about, some of whom Davy does talk about, I really don't quite see what Davy's trying to achieve with this experiment, other than using a new piece of kit that he's suddenly got access to because he happens to be in Florence.
Yeah, good question. Is he not trying to show that diamond and charcoal are made of the same thing? So that's not a conclusion that Lavoisier actually draws. He says that they're both combustible substances.
Mm-hmm.
So his conclusion is that diamond needs to be reclassified. It's not a stone, but a combustible substance.
Okay.
And he spends a lot of time comparing it to charcoal, but he doesn't come out and say that charcoal and diamond are made of the same element or the same substance, at least not in these 1770s experiments. So there was an extra step to take after those 1770s experiments, which consisted in being more precise about what diamond was made of.
Okay.
Is that what Davy is doing?
I think it may be, but he can be pretty opaque when he puts his mind, or even when he doesn't put his mind to writing about it.
Yeah. But I'm really interested you bring up the Florentine experiments, because they're a part of the story which I haven't explored very much, but which is very interesting. There's experiments done in Florence. There are also experiments done by the Holy Roman Emperor, which are then reported by Henkel and included as a very long footnote in they're briefly reported by Henkel and then elaborated upon in a very long footnote by Dolbach in his translation of one of Henkel's works.
Right.
And which by that route are picked up by other French chemists without those chemists knowing much about the details of the earlier experiments. So the whole Florentine dimension is an interesting part of the story that someone else needs to look at in more detail.
Well, I'm looking at the sort of daily part of it. Okay, we've got questions coming into the Zoom chat box. The first is from Nicholas Zamburiadis. Would you like to ask the question, Nicholas?
I can see the question, so I could just respond to it.
Okay, fine. Carry on.
Yeah, really interesting question. So if the interactions between the crafts were important, what was driving those interactions? So I've given one example or one hypothesis for the 18th century, which is that the rise of mining schools, which employed trained chemists, helped to draw in pharmacists who brought their techniques with them. And so you get this kind of hybridization of mining and pharmaceutical techniques. Could recipe books be a similar driver of these interactions? And I think the basic answer is yes. The recipe books I've looked at from the 18th century are by definition very varied. So the one I've looked at is Jean Helot, French chemist from the first half of the 18th century, who has left his notebooks at Caen in a library there, and which cover the whole raft of different crafts. I guess the question is whether this was just a matter of juxtaposition, like putting one craft next to another, or whether it's generally a matter of synthesizing them, combining them to produce new things. That will be my question for other people who know more about recipe books.
May I offer an example of the behind my question is the following example. I've recently studied Antonio Neri's recipes and comparing them to archival material at Meissen, which I admit is not easy to get to, so I don't blame anybody for not getting to it. But there are Herold's writings on various pigments are very similar. In fact, the phraseology is very similar to actually Neri's or even original Italian phraseology about making particularly green and also red pigment. Green as copper green and iron red as iron red. And I personally think the bridge has been the translation of Neri's work into German by Kunkel. And then that went, and Kunkel was a friend of Böttger's, by the way. And even though Herold came to Meissen after Böttger, probably the books were around and Herold. But this is just a conjecture on my part, so I wanted to ask your view on that. And then I have another question I wanted to post.
John Christie's got a question, so sure.
I'm sorry? Yes, of course. Yeah, go ahead. I'll post the question and whenever you get to it.
John.
Okay, first of all, Michael, thank you very much for the paper. I found very, very interesting and original. I particularly like looking at your long Vauquelin footnote and just the very, very prominent position Klaproth has in it, and how valued his analytical techniques were and rapidly translated into French. My question is, well, as I've said, about sharing knowledge and technique, yeah? And the way you've presented things, this just, it kind of happens in terms of things coming together. There doesn't seem to be a difficulty about sharing particular techniques and knowledges. But if we, say, introduce the second of your book title terms, value along with matter, does everyone just happily give away their techniques? These are valuable. Making porcelain, you know, all the high temperature stuff. But the way the information all you've got, I'm not doubting any of it at all. It just seems a kind of free exchange, as it were. But could it have been so simple? when crafts are renowned for sequestering their techniques?
Yeah, very good question, and I get your point that the impression I have given is of a very smooth flow of ideas and people across Europe, which is not the impression I really want to give. Obviously, there was all sorts of difficulties. There's another version of this paper which is all about translation and new journals, and definitely a lot of conflict, especially involved in trying to reconcile Swedish chemistry with French mineralogy, which was really, really tricky. And there were definitely lots of debates about that. But you're not talking about just debates or about whose science is the best. It's about what becomes public.
Yes.
What is, and who gets to know what. So because of the sources I've looked at, I've obviously only found examples where people are willing to show things.
Yeah. No, I just asked the question because I've looked at analysis, say, of mineral waters, and what I find there is retention of knowledge rather than sharing at times, yeah, and with other things as well.
Yeah, I think what I would say is that when things were shared, often this is because scholars were involved as well as artisans. So I think it's a good rule of thumb that scientists, quote unquote scientists, employed at national academies in this period were more inclined to share trade techniques among themselves than practicing artisans were.
Yeah. Okay, that's most helpful. I want to give other people a chance to ask questions. I just thought it was a terrific paper. Thank you, Michael.
Thank you.
Back to you, Nicholas.
Yeah, okay. Let me, well, somewhat cryptic message, I'll tell you. There is a reference in the so-called Steinbrück Bericht, a report that was Steinbrück, the inspector of Meissen, periodically published, and of 1719, I believe it's particular. And he actually there recollects a very brief, in a one sentence, a debate between Böttger and Tschirnhaus about something that we might call this compositionism. And I'll just give you the quote. It's very brief. Böttger says, Tschirnhaus thinks that if he heats porcelain, he can decompose it to its constituent parts. However, he himself didn't believe that was possible. That's a very brief sentence hidden in the Steinbrück Bericht, which I thought might be relevant to this discussion, to your query. I don't know what you think about that.
Actually, I've looked a lot at Réaumur and his efforts to imitate hard paste porcelain in the 1710s and 1720s, and his approach is always the opposite in the sense that he's not trying to decompose porcelain, real porcelain, to work out what the components are. That doesn't seem to cross his mind. What he's interested in doing is almost the opposite. He's interested in trying as many raw ingredients as he can and working out which work, basically.
Which was the name of the person you just referred? I missed the...
René Réaumur.
Oh, yeah, Réaumur. Yeah, okay.
Yeah.
Of the temperature scale.
Yes, I understand.
So it actually hadn't occurred to me that that's one way of attacking the problem. Just to take some real Chinese porcelain and try to divide it into its components.
Apparently, and that's the only place I came across that myself, is that according to Böttger's writings, Tschirnhaus tried.
Okay.
I don't normally ask. I normally ask for volunteers, but I'm going to volunteer someone because I think he should ask a question. As Adrian, how does this fit into your views on the chemical revolution? Sorry to put you on the spot.
Can you hear me?
Yeah.
Good. I don't really have a view of the chemical revolution, except to say that Well, the view I have I have a view of the quote the chemical revolution, unquote. That is our concept of it, and that view is somewhat skeptical and critical. But putting that aside, I very much welcome everything Mark has been telling us, because at the very least, it tells us, and a wonderful paper, Michael. At the very least, it tells us there's a hell of a lot more going on than the Lavoisier story, phlogiston story, and so forth. And it's rather different. What you're telling us is rather different, though it has some affinities with it. Sorry, that's not a very good answer to your question, but thank you for giving me the chance. I don't know what you think, Michael, about that.
Yeah, I guess I don't have a general, a strong general opinion on the chemical revolution. I'm happy to observe the debate from a bit of a distance and then use it for my own purposes, which are to show how different crafts interacting help to drive chemical change. At the same time, I can't help noticing that the decomposition of gems happened very quickly in exactly the period when the compositionist revolution is supposed to have happened. So I would have no objections if anyone used my study of gemstones as grist to their mill for the existence of a chemical revolution, or for the notion that the revolution was defined by new notions of composition. I think my caveat would be, think about the differences between different materials. So just because this happened for gems in this period doesn't mean it was happening for other materials at the same time. So neutral salts, for instance, based on work by various people, it seems to me that neutral salts had already been given a compositionist treatment by about 1750. So this was something that was worked out by people like Omberg and Elo at the Paris Academy of Sciences in the early part of the 18th century. And if you look at mineral waters, for instance, already in the 17th century, you find really thoroughgoing efforts to divide mineral waters into their components and measure the components and then put them back together again. So depending on which material we look at, we're going to get different answers to the question, when did compositionism begin? I think that's consistent with saying that there was a chemical revolution, but it suggests that it may have been a result of adapting earlier techniques to new materials rather than a completely new phenomenon.
Okay, thank you. Michael Jewis, you have a point to make. You're muted. Oh, look, there you are.
Right. I'm reverting to your first question. What was Davy up to, wasting diamonds that late? And the question wrote, Michael said that when Lavoisier was first working on diamond, he didn't realize it was chemically the same as charcoal. And I've just pulled out his 1789 Elements of Chemistry. And in his list of simple substances, he's got charcoal, diamond isn't there, and flicking through the various pages about combustion of charcoal, I can't see any mention of diamond. So I don't know when people finally decided they were the same. At least I can't see it in Lavoisier of 1789. I don't know whether anyone else knows when people finally decided that was the case, because in principle, all you've got to do is burn the two things and note that the gas that comes off is exactly the same. It's a fairly easy thing to prove, provided you think of doing it.
Yes, so you would think Lavoisier would have done that, because that's exactly what he was doing for other gases. And I really should know the answer to your question, given that I've just spoken about Lavoisier's experiments, but I don't. There may be others who've done the research on the later history of diamond combustion.
Okay, so perhaps I'll just close off with one last question. One of the things I've been doing on Davy is, oh, sorry, John, you want to know? John, carry on.
If I may, just following up from some of Michael's thoughts, you know, it depends on the range of substances. If you're thinking about things in the compositionalist sort of a way, and I was just thinking back to some of Ursula Klein's work. All the examples we've been looking at are the minerals, their earth, salts, etc., etc., etc. I wonder if much greater difficulty, this is drawing on Ursula's work, attends composition of vegetable matters. And that might be a wholly different case. I just wondered if you had any thoughts on that, Michael.
You're right to raise my main thought. You're right to mention Ursula Klein and Wolfgang Lefebvre's work on 18th century materials, because in fact that is one of the few studies where I see a fairly serious effort to compare and contrast two different materials and genuinely contrast them. I guess my only caveat is that I couldn't find any examples in their work of the two coming together.
Mm-hmm.
Techniques from plants being transferred to minerals or vice versa.
Mm-hmm.
And I suspect that may be one engine of change in 18th century chemistry, partly brought about by this influx of apothecaries into mining centres.
Yeah,
people trained on plants all of a sudden being
no, that would be a good location to examine this question. Yeah, thanks. That makes sense, Michael. Thank you.
I mean, that's a really, really interesting point. And again, thinking of Davy. Davy was trained as an apothecary in Penzance, and then later went into the mining industry with the safety lamp. I never really occurred to me until now to sort of think about what sort of connection there is going on there. There must be something. Okay, so with that, I will draw things to a conclusion. The next seminar in this series is on the 26th of March, when Larry Principe will be talking about his new edition of Sources. Then on the 20th of March, we've got the SHAC postgraduate meeting early, career research 3-year meeting, which will be in Amsterdam on the 20th of March. That should go up on the Adelard Pearson website tomorrow, and it'll be circulated through the usual SHAC channels in the course of next week or so. And then on the 10th of April in Oxford, Maison Francais, we've got the Memory Bill Brock meeting. That's been advertised. There's no registration for that, but do send me an email so that we know you're coming and we can work out how many coffees to order for the meeting. So it just remains for me to thank everybody involved in organising this seminar, which is does take quite a few people to sort of bring it to the screen. That's Anna Simmons, Rob Johnson, Caroline Cobbold, and Johan Tau, who has been running the all the electronics to bring the seminar to the screen. But most of all, to thank Michael Bycroft for giving us a really, really interesting seminar, and I shall look forward to getting hold of a copy of your book in the next week or so, 2 weeks or so. So thank you very much. Have a rest of a good day, evening, night, wherever you happen to be in the world, and hopefully see you at the end of March for Larry's seminar. Thank you.
Thanks very much, Frank. If you don't want to read the whole book but just want a sneak preview, you can go to the links which I've just put in the chat. One is a blog post and the other is an essay in the New York Review of Books.
Okay, right.
Thank you.
Okay.
Thanks for all the wonderful questions.
You're very welcome. Okay. Thank you, everybody. Thank you. Oh, she's gone. So there you are. Thank you, Jan. That went
No
very
worries.
smoothly.
There was no question from YouTube, just so you know.
Yeah.
So I'm gonna end the meetings now. But
Okay.
very nice to meet you all.
Thanks very much. Thanks for your questions, Frank and John.
Okay.
Cheers. Thank you.
Thank you, everybody.